In the popular imagination, a black hole is simple. A bottomless pit in space. A cosmic vacuum cleaner, sucking in everything nearby. But space is rarely simple. And here, at the edge of physics, nothing works the way you expect. A black hole is not a hole. Not an object, either in the usual sense. It is a region. A patch of space-time so warped that even light cannot escape. Cross a certain invisible boundary, and every path you can take, every possible future, bends inward toward a single fate. This is the event horizon. To us, it looks like a dark sphere, floating in a sea of stars. But that surface is not solid. You could fall through it without feeling a thing. No impact, no sudden flash, just the quiet, unstoppable tipping of a universe beneath your feet. From far away, though, your fall looks very different. To a distant observer, you never quite cross the edge. You slow and dim and freeze in time, painted on the horizon like a ghost. Two journeys, two stories, both true in the language of relativity. Already, the black hole is breaking our common sense, and we have only reached its surface. Because to understand what really lives inside this darkness, we must rethink gravity itself, not as a force that pulls, but as a shape that bends. Next, we step closer into the geometry of a universe that folds in on itself. Gravity, as we learn it, is simple. Mass pulls on mass. The more you have, the stronger the pull. Einstein replaced that picture with something stranger. He told us, mass doesn't pull. It tells space-time how to curve, and space-time tells matter how to move. Planets, stars, you, me, we are all sliding along the curves of a four-dimensional landscape. Most of the universe is gently sloped. Fall toward Earth, and the curve is mild. You can still climb back out, but add enough mass, crush it into a small enough space, and the landscape goes vertical. The escape routes vanish. At a certain radius, the escape speed reaches the speed of light. Nothing can move faster, so nothing can leave. That radius has a name, the Schwarzschild radius. For a black hole with the sun's mass, it's only about 3 kilometers. The sun squeezed into a city. This is already unsettling. The same star, the same mass, but a completely different fate for the surrounding universe. Outside that radius, gravity behaves as usual. Orbit far away, and you may never know a black hole is there. It does not chase you. It does not hunt. Come too close, and the geometry takes over. Not because the black hole is greedy, but because space and time have been bent into a one-way funnel. And as you fall, time itself will begin to act in ways that defy everyday experience. In the next chapter, we watch clocks break and distances lose their meaning. At the edge of the abyss, imagine 2 clocks, one strapped to your wrist, one floating far from the black hole, safe in quiet space. You step from safety and begin your fall. For you, time feels normal. Your heart beats. Your thoughts flow. Seconds pass with ordinary calm. But from the distant clock's point of view, your time is slowing. Every signal you send, every flash of light, is stretched into longer and longer wavelengths. Redder, weaker, farther apart. This is gravitational time dilation. The deeper you go, the slower your time runs, relative to the universe outside. At the event horizon, the effect becomes extreme. To the distant observer, you never quite arrive. Your final moments are frozen, smeared into an eternal, fading flicker at the edge. For you, it's different. You cross the horizon in a finite time. No drama, no wall of fire, just a boundary you only recognize in equations. 2 realities, never reconciled by a single shared view. Our intuition demands a single story. Gravity refuses. Inside, the geometry tightens. If the black hole is small, tidal forces stretch you, head to toe, into something thin and long. Spaghettification, a word almost playful, for a process that tears atoms apart. In larger, supermassive black holes, The tides ease at the horizon. You might drift in intact, with no immediate sign that you've crossed a point of no return. But whether you feel it or not, your future is sealed. Further in lies the place where our theories truly fall apart. Next, we journey toward the center, to a point our mathematics calls a singularity. The singularity. The word suggests a place, a dot, a sharp needle of infinite density, at the heart of the black hole. In our equations, it is where curvature becomes infinite, where space-time bends so violently that the numbers explode. But infinities are a warning sign. They do not describe reality. They describe the failure of our tools. General relativity, our theory of gravity, works on large scales with exquisite precision. Quantum mechanics, our theory of the small, rules the world of particles with equal success. Yet in the core of a black hole, both must speak at once, and neither knows the language of the other. Here, our best map of gravity meets our best map of the quantum, and both tear at the edges. Does matter truly collapse into an infinitely small point? Does space-time end? Or does some deeper, unknown theory smooth out the singularity into something we do not yet have words for? We invent possibilities. Quantum foam, Planck scale cores, exotic states of matter and geometry. But for now, they are only sketches on paper. What we can say is this: no signal, no information can ever escape from within this inner region to tell us which story is right. The singularity, whatever it is sealed off by the event horizon. Physics itself becomes local and silent. So we turn back to the horizon, to the only surface we can see, and we ask a new question. If nothing can escape, how can a black hole ever change or give anything back to the universe that created it? In the next chapter, we discover that black holes are not as perfectly black as we once believed. Look again at a black hole in the real universe. It is almost never alone. Gas spirals toward it, heated by friction to millions of degrees. An accretion disk forms, a glowing whirlpool of plasma, circling the darkness at relativistic speeds. Magnetic fields twist and snap. Jets of particles burst from the poles, screaming into space at near light speed for thousands of light years. Paradoxically, black holes can be the brightest objects in the cosmos. Quasars, powered by supermassive black holes in distant galaxies, outshine all the stars around them combined. Yet, the hole itself remains dark. The light comes from just outside the edge, from matter fighting its final battle with gravity. In 2019, we saw that edge. The Event Horizon Telescope stitched together radio eyes across our planet, forming an Earth-sized mirror to capture the shadow of a black hole. Not a photograph of the hole, but of its absence, a circular silhouette carved out of a blazing ring of gas. This image confirmed Einstein in ways he could never have imagined. The shadow's size, its shape, the way the light bent around it, all match the predictions of curved space-time. But there's another kind of glow, much fainter, born not from infalling matter, but from the quantum vacuum itself. Stephen Hawking showed us that when we mix quantum physics with curved space-time, black holes are not entirely black. They radiate. In the next chapter, we step into this quantum haze, where empty space boils and black holes slowly leak away. In the quantum world, empty space is never truly empty. Pairs of virtual particles flicker into existence and vanish, borrowing energy from the vacuum. For the briefest of moments, near the event horizon, this restless foam meets extreme gravity, and something strange can happen. One particle can fall in, the other can escape. To a distant observer, it looks as though the black hole has emitted a particle. It has lost a tiny bit of its mass. This is Hawking radiation. The black hole shrinks, imperceptibly at first. For stellar giants, the process is glacial. For supermassive black holes, it is effectively frozen in cosmic time, but left alone for unimaginable ages. Even the largest will evaporate. This leads to a deeper puzzle. What happens to the information about everything that ever fell in? In ordinary physics, information is never truly destroyed. rearranged, scrambled, hidden, but not erased. Yet a black hole that evaporates completely seems to take its secrets with it. The quantum state of every star, every particle, every photon, reduced to a featureless puff of radiation. This is the black hole information paradox, a clash between quantum rules and gravity's geometry. To resolve it, physicists have proposed radical ideas: holographic universes, where information is encoded on surfaces, firewalls at the horizon, subtle correlations in Hawking radiation itself. None are fully proven. All remind us that black holes are not just astrophysical objects, but laboratories for the deepest laws of reality. In the next chapter, we strip black holes down to their simplest description and find that beneath their apparent simplicity may lie unimaginable complexity. From far away, a black hole is astonishingly simple. According to the no-hair theorem, it can be completely described by just three numbers: mass, spin, electric charge. No surface features, no scars or patterns, no hint of what formed it. A star, a cloud, a chaotic storm of radiation. All roads lead to the same smooth geometry. It is as if nature erases the past, leaving only a perfect minimal shell of curved space-time. And yet, if information is not truly lost, this simplicity must be an illusion. Somewhere in the quantum structure of the horizon, in the tangled fabric of space-time itself, the details must be hiding. Physicists imagine the event horizon not as a bland surface, but as a seething, microscopic tapestry of quantum bits, each bit encoding some whisper of what has fallen in. To us, it still looks bald. No hair, no trace. But in the mathematics of holography, a strange idea emerges. The three-dimensional interior of a black hole may be fully described by information living on its two-dimensional boundary. Volume, emerging from a surface. Reality, from a kind of cosmic code. We do not yet know how to read this code, but we can listen to black holes in a new way, not with light, but with ripples in space-time itself. In the next chapter, we watch black holes collide and hear the universe ring like a struck bell. For most of human history, the universe spoke to us only with light, visible, infrared, X-rays, and radio waves. Then, in 2015, we heard it. Two black holes, each dozens of times the mass of the sun, spiraled toward each other, over 1 billion light-years away. As they danced their final orbits, they stirred space-time itself. Ripples spread outward, gravitational waves, predicted by Einstein a century earlier. On Earth, the LIGO observatories waited. Laser beams traveled down kilometer-long tunnels, bouncing between mirrors with almost impossible precision. When the waves passed through, they stretched space in one direction and squeezed it in another by less than the width of a proton. Just enough. The detectors twitched. Music, brief pause, then a soft chime. From that tiny shiver, we reconstructed a colossal event. Two horizons merging, their masses combining. A portion of their total energy radiated away in a fraction of a second, as pure distortion of space-time. For an instant, the power output exceeded that of all the stars in the observable universe. Yet the merger itself was silent, dark, invisible in ordinary light. Black holes, the ultimate sinks of radiation, announced their presence through the flexing of reality's fabric. Since then, we have heard many more, a growing symphony of collisions, each adding notes to our understanding of how black holes form, grow, and shape galaxies. And still, the most unsettling questions remain. To face them, we must pull back one last time to the scale of the entire cosmos and ask what black holes mean for the ultimate fate of everything. Fast forward through unimaginable ages. Stars exhaust their fuel. Galaxies dim. The universe expands, cools, empties, in some visions of the far future. Black holes are the final architects of structure. They swallow the last wandering stars, the stray gas, the frozen remnants of once warm worlds. For a time, the cosmos is a dark archipelago of black holes, isolated in a vast, growing ocean of nothing. Then, even they begin to fade. Through Hawking radiation, they leak their mass back into space, as a thin mist of particles. The larger the black hole, the longer this takes. For the giants in galactic centers, the process dwarfs the current age of the universe by a factor beyond comprehension. But if our theories hold, there comes a day when the last black hole evaporates. What remains? A cold, dilute universe, filled with low-energy radiation, and the faint echo of everything that ever was. Did the information survive, subtly encoded in the outgoing radiation, or did black holes truly wipe the cosmic slate clean? We do not yet know. Black holes sit at the crossroads of our deepest theories, refusing to fully belong to either. They are not just objects out there in distant galaxies. They are tests of our understanding of space, time, and reality itself. Nothing about them works the way our intuition says it should. And perhaps that is their greatest gift, to remind us that the universe is stranger, subtler, and more beautiful than our first ideas allow.